Hi, everyone. My name is Ken Goldberg. It's a pleasure to welcome you back to the Citrus People and Robots Initiative lecture series. And we are being live streamed actually out on the web and recorded for future reference. So this talk will go into the archives for the rest of history. And we have actually, I want to say thank you to Ron and to everyone involved with the Dreams seminar, who has been coordinating the rest of the talks that we're going to be having every Monday. So this is an extremely great semester. We've got a great lineup of speakers, both from internally and externally, who will be speaking. And that I will be sending out the full listing on a regular basis. And by the way, if you're not on the mailing list for this series, please mention this to Ron, who can add you. Then you'll get notices every week. Now, our first speaker of the series is I'm extremely excited about, and it's because I have a personal connection with him. Jeff is I should say Dr. Mahler, just completed his dissertation and was working did this work in my lab, and he did his undergrad at UT Austin, and then started a company with a group of other colleagues there. They did very well with that. It's in 3D point cloud processing, and that turned out to be an ideal background for him here at Berkeley, where he came in as an EEC student and did a huge amount of work in grasping and combining sensing with the actual modeling of manipulation. He also had the pleasure to work with Professor Baichi on her course, and that actually led him to really become an expert in manipulation and the theory of the analytic approaches to manipulation. And so the combination of those he's put together with deep learning, and the result has been, I would say, somewhat spectacular. So he's been getting a lot of coverage in the press, and among companies around the world are very interested in the work that he's doing. He's won some best paper awards for his work. He is exemplary, I would say, as a student, writing papers that are usually, when he writes a paper for a conference, it's really the equivalent of 3 papers packed into one. And the reviews attest to that. He just turns out amazing publications. So please welcome Jeff Mahler.
So the ability for robots to grasp and manipulate a wide variety of objects is extremely useful in many applications. For example, warehousing, where robots will need to handle a wide variety of consumer products that can come disorganized from storage. And flexible manufacturing systems where new industrial parts might be designed and a manufacturing line will need to quickly handle those parts. And even in the home, where robots will need to manipulate cluttered and novel objects that people bring in, like books, cups, fruits, etc. And nonetheless, today, even relatively simple grasping tasks are done by humans in industry, such as packing square boxes. And one of the reasons for this is it's very difficult for robots to deal with inherent uncertainty due to sensing, physics, and control. And even Rod Brooks, who founded Rethink Robotics and created the Baxter robot, who many of you may be familiar with, has said that the ability to grasp and manipulate millions of different size and shaped objects remains a grand challenge for robotics today. So today, what I'll first do is give some background on the context of this problem and what my thesis was about, then go over a few of the main topics of the thesis, and finally end with some discussion of the implications. First off, some context on the grasping problem. So some might argue that grasping has actually been studied since about the 1880s. And most of the research between now and when it started was on what we call analytic grasp planning. So we assume that a robot has some perfect knowledge of the state of the world, such as the exact shape and mass of objects. And the goal is to, given such state representation, plan a grasp or set of contact points on objects in order to maximize some reward function. And the reward function might include characteristics that are deemed to be desirable, such as bounding the mobility of the object, so geometrically constraining the object, the ability to achieve a static equilibrium, so counterbalancing external forces and torques, or to achieve dynamic stability through compliant control at the fingertips. But in practice, it was found to be relatively hard to use these methods in certain cases because these methods assume a separate function, state inference function, that given some observation, such as an image or even tactile data of the world, will infer the state, such as the shape and pose of an object in the world, and use that to plan grasp given that perfect state knowledge. And one of the reasons this is so challenging is because when robots are operating from images like this, they're dealing with significant amounts of occlusion, overexposed regions, corrupt pixels, missing data, and depth images. And there's another fundamental problem in addition to sensor noise, which is the fact that this problem is partially observable. If the robot only sees, say, a finite number of viewpoints or there's objects behind clutter, the sensor data does not actually contain full information about the object shape. So this makes it very difficult for robots to actually infer the identity, shapes, poses, mass of objects in the scene. So another trend that started in robot grasping was a little different and based on deep learning instead, considering the problem of whether or not robots could predict good grasp directly from sensor data such as images. And this is building on research and exciting results in the computer vision community where growing data sets leading up to the 14 million images in ImageNet led to remarkable results in image classification. And furthermore, results in games allowed deep neural networks to beat human players in Go, for example, and even perform very well in machine translation. So to formulate grasping as a problem that can be used, that deep learning can be used for, the way it's typically formed is as to have an input image of some object the robot wants to grasp, and for the deep neural network to actually run a set of convolutional filters. You could even think of this as a filter bank detecting different oriented edges, for example, or different templates, and predicting the success of various grasp hypotheses in the image. So here is one architecture predicting grasp hypotheses as different angles in the image. And there's been a large amount of work on this topic. The way that this problem is more formally written down is to learn the parameters of a neural network that minimize some loss function. So let's call the neural network here Q, parameterized by some weights theta. It takes as input some image and grasp, and the goal is to predict the reward or some success metric on that grasp, given a large data set. And then given this function that it's able to predict the success of various grasps in the image, online, the robot will choose a grasp that maximizes this output by searching over a set of available grasps in an image. However, one challenge with this method is that it requires one to have this large data set for which to optimize over and actually learn this grasp quality function, Q theta in the previous slide. And two things that have been considered over the past 5 years were human labeling, where humans sort of painstakingly draw bounding boxes on specific images. One notable data set from Cornell has 1,035 images and could lead to about 80% success on grasping these objects in the same setup. So labels for the same objects that the robot has to grasp and in the same environment. And empirical or self-supervised data collection, where robots will actually experiment and label their own grasps and over time iterate and converge towards a quality function that is able to predict the real outcomes of its grasp attempts. So one study in my Google had 1 robot year of data collection with 80 to 90% success, which is exciting, but the cost of data collection makes it very difficult for people to replicate this in other setups, especially because these data sets do have to be collected, at least at this time, for every new robot, sensor, even potentially for new objects that the robot has to encounter. So the goal in this work is to look at the empirical grasp planning objective of learning this quality function and consider how we can learn it more efficiently. And the idea behind my thesis is not to approach this problem so much in terms of a learning algorithm, but actually to think about, okay, what is this expectation being taken over in the first place? Expectation is with respect to some distribution over rewards images that the robot's likely to see based on positions of the camera and different objects and different configurations that it's likely to have to interact with, and what kind of grasp it'll have to deal with. And this depends on parameters of the sensor, how we specify controls, whether or not that's motor torques or just setting end effector positions for the gripper to go to, how the hardware is calibrated, how we'd choose to reward the robot, whether or not a success is lifting and moving an object, holding it while shaking, and even cleaning data, collecting data from humans or empirically can lead to a lot of mislabeled examples, and often requires one to actually go back and fix labeled data to get things to work. And so to do this, I actually asked the question, okay, well, how could we maybe automate this process, construct some distribution computationally from which we can sample reasonable training data in a matter of days or hours on a standard computer instead of on a real robot or from humans. And so we revisited these physics-based reward metrics, which had limitations about certain assumptions, but actually had some benefits in terms of being able to be scalable, interpretable. We could relate the successes we get back to an actual model generating the data. And we could actually, in many cases, run tests on these reward functions to make sure that they were doing what they're supposed to do. And so the question is, well, then how can we get these to work in the real world? The hypothesis behind this work was that we could build upon ideas for transferring from simulation to reality based on randomization. So this idea has been around arguably for quite a while. In grasping, there's been an idea of randomizing over a pose, shape of objects, and frictional parameters in order to plan grasps that work better in the physical world. And now we've seen a surge of these ideas in the deep learning community from projects like CAD to RL, where we could train quadcopters to navigate in simulation, and even a recent OpenAI result, which I think many people have seen, where they're able to train a multi-fingered hand to reorient the cube just based on simulation and randomizing over physics. This gives another level of robustness to the learned policy. So my thesis is that grasp quality functions can actually be learned efficiently from synthetic training data sets, generating from stochastic models based on contact mechanics, image formation, and large data sets of 3D object models. And the main sort of workhorse behind this is a project called the Dexterity Network, which is a framework for actually synthesizing such training data sets from repositories of 3D model. And we have code and data available at the URL here. Okay, so now I'll cover the two main topics behind the thesis. The first is how we built up an initial model for generating these training data sets. In the first instantiation of the Dexterity Network, we've examined the problem of whether or not we could generalize to new objects by actually leveraging a large repository of 3D object models. So we first carved off this one portion of just looking at generalization to object shape, and without actually studying how to do deep learning directly from images to predict grasp, but actually indexing into this database to look up a similar 3D model based on some image of the world, say, where we can then pull down pre-computed grasp and execute the best grasp for a similar object on the real robot. And to study this problem, we leveraged the growing data sets of 3D models available on the web. For example, new objects being generated for 3D printing on Thingiverse, as well as data sets being generated by researchers such as Scan Datasets, the YCB Yale CMU Berkeley dataset, which is a collaboration with Peter Abiel and some others, and then KIT database, as well as big synthetic datasets such as ModelNet for shape recognition. And with James Kuffner and some other folks at Google, we built a distributed system for actually performing grasp analysis across tens of thousands of these 3D CAD models, actually, with up to 1,500 virtual instances sort of analyzing grasps on these CAD models at once. So essentially, each computational node here is getting a subset of 3D CAD models and running a simulation for that, then adding data to a central database. Via this computation, we generated the Dexterity Network 1.0 dataset, which contained 10,000 3D object models and about 250 parallel jaw grasps on each object, specified as pairs of contact points on the 3D mesh surface. We've labeled each of these with the probability of force closure, which is essentially looking at whether or not the grasp under certain quasi-static conditions can resist any arbitrary force and torque applied to the object.
When you generate this parallel jaw grasp, do you also assume different materials?
Yes, so that's where the probability comes in here. So what we're doing actually is randomizing over the material properties, but basically the friction coefficient here. So we assume the objects are rigid.
What about weight?
So for the force closure metric, the weight actually doesn't come into play, but the pose of the object does. So we randomize over where the sort of relative pose of the hand and object.
Of course, it would be probably easy to add the weight, the gravity forces.
Right. We have some randomization over that in the modern version of the system that I'll talk about closer to the end.
Yeah.
Mm-hmm. Okay, so we in the Dexterity Network 1.0 looked at this question: could we learn to actually predict the probability of force closure for some new object given the database? So the idea is that if the database already contained 2 spray bottles like this, and the robot gets a new spray bottle, can it learn to pre-predict how good each grasp is going to be based on some features of these objects? And maybe also based on how close 2 grasps are to each other on the same object. And we did find this to be true. Basically, we found that a fairly significant acceleration, especially as the number of prior CAD models grew. And this was not too unexpected because as larger number of CAD models exist in the database, there's more likely to be some similar object to a new object to compute grasp for. But I want to skip over this quickly because the work published in the paper was actually only in simulation. And I think what's more interesting is to consider what happens when you run this method on the physical robot. That motivated a lot of the later work. So shortly after we published it, we got a Zymark Zymake, which is this 4 degree of freedom robot, and an ABB Yumi industrial bimanual robot that can reach poses to width about 0.1 millimeters. So we built this sort of fancy perception system that could use deep neural networks to index similar 3D objects. I won't go too into details there, but what we essentially found is that the registration system, when given a known object, so if the database already contained the object that the robot was trying to grasp, we could find the object's translation is posed up to about 4 or 5 millimeters and within 3 to 4 degrees of rotation within the plane. So we knew where the object was pretty well. And when we have such a system, even a clunky robot such as what's in this video could execute fairly precise grasps, such as this one on this 3D printed industrial part. But unfortunately, it became challenging to extend this system to index similar objects from real sensor data. So here's one failure mode that we observed when we had 12 known objects, subset of 4 of which are in the bin. And the robot predicts the wrong object here with a little sort of handle in the back side of the object and actually grasps an empty space, which is extremely dissatisfying. And when the robot didn't have knowledge of what objects are there, things could be even worse. So this is showing attempting to match this large bag clip to a data set of about like 1,500 3D CAD models. And as it turned out, despite how many CAD models we have, there's nothing that was quite similar to this. And the grasps were failing very often. So I asked the question, okay, well, why is this failing? And my hypothesis was at the time that maybe by matching global shape, we're sort of asking the perception system to do too much. Shapes can vary, and objects in general can vary by large amounts and still be grasped in similar ways because they have similar sort of affordances, such as handles or opposite-facing parallel surfaces, antipodal surfaces. And we realized is that if we leverage modern point cloud registration systems rendering synthetic depth images, we could actually relate grasp points on 3D CAD models to pixels and orientations in image space, instead of looking up from this image to go back to the world where we know the CAD model and its pose in the world. And this illustration I put up here because I wanted to show that what actually happens here is that if we look at the quality of different grasps on an object such as this, and here we look at the orientation of this gripper, we slide it around the image and look at the quality of each grasp specified by the center pixel here, we actually get this function that gives us a map of the probability of success for different grasps without actually exactly defining this function in image space. So this led us to the DexNet 2.0 approach, which was to leverage a model that jointly computed robust grasp on 3D CAD models and rendered an associated grasp with image space to train a deep neural network to predict the quality of grasp directly from images. And the approach we broke into 3 parts. First, generating a training data set. Second, learning to predict grasp quality from the images in that training data set. And finally, searching for the grasp with the highest quality on the physical robot. Mm-hmm.
On your point too, how difficult would it be to add to your learning of grasping with respect to functionality? Because depending on what the function, what you want to do with the object, you will change your grasp. And the grasp that you and I taught 2 years or 1 year, whatever it is, strictly analyze the stability only.
Right.
While in regard, what the purpose is, how difficult that would be to include the functionality?
So that's a great question, and I think it's very task dependent, essentially. So there's certain, right.
Except that certain geometries are amenable for certain tasks and others are not. So that would be another classification on your part.
Right.
See what I'm saying?
Right.
I mean, if you have chopsticks, they will not be able to cut. They will be doing what the scissors can do.
Right.
Or for that matter, a knife, unless it has sharp edge.
Right. So I guess you're saying there's a whole other problem of discovering which task you can use an object for. Yeah.
There you go. You can have another creation.
Right. Yeah. This is certainly not solving the problem of grasping in general, but it's a very interesting question because there's a trade-off between specifying these very generic sort of reward functions that are saying, okay, can a grasp resist any force and torque on an object, and having a reward function that's actually guiding grasp towards some very specific task.
Industrial application, things are limited, and that's the beauty of industrial application. So it's not everything and anything. So if they want you to push, peg and hole, then you know what the functionality is. So
right.
Possibly, I think that could be easily implemented here.
So if I understand correctly, what you've done is you said, well, we got a training data set from whatever method, right? Which right now is your simulation, but you're saying we're taking the neural network and having it spit out a value function for the different grasps.
Yeah.
Right? And then afterwards you're then saying, well, we take our normal physics and our camera to determine to get a robot to actually execute the grasp. But right, so you can take this and say to as long as your training data set has the labelings of the value that you're interested in, right, you could use it with any value, like any grasp scenario. So if someone labeled it to be, a simple example would be you manually label, this is how a human would grasp this object.
Right.
I mean, your neural network predicts.
You can label it with some preference is given that particular task.
Right.
And then this translates to any task, right? As long as you have labeling support. Is that correct?
Yes. So one thing, a hammer is a good example, right? And generally, where you want to pick up a hammer, the safest place is right around the head of the hammer, right? To minimize. But actually, it's the worst place if you want to hammer a nail. So we could certainly, actually, a nice extension would be to, as you suggest, is go back and now re-edit those grasps in terms of functionality.
That's right.
And then once you have that new set of examples, you can really train a new network.
Right.
And try to identify those. Yeah. And there's been some work on this. Animesh has a paper on,
right.
Animesh and Andre over at Stanford have a project on exactly this.
Okay, sorry to interrupt.
No, I'm glad you brought that point up. I want to be clear that we've studied one case here where we can automatically synthesize these data sets, and extending to other tasks would require some redesign. Okay, so I'll jump in, try and quickly cover this section. The basic idea behind generating the data set was to formalize it as a graphical model that we could sample training data from. And specifically, we broke this generative model of training data into 4 parts. Some model for the states that the robot's going to have to encounter. So this could include the different 3D object shapes, their masses, their material properties, and then where they sit in the world. So are they by themselves on a table? Are they in a heap or on shelves? An observation model that, given a state, produces some virtual sensory data corresponding to that state. So here that's going to be synthetic depth images. And actually, we augment these with synthetic noise in DexNet 2.0, which is not shown in this image. A model for generating grasp candidates. So some distribution to guide grasp sampling towards promising areas, not just evaluating grasps that are floating in air, but actually contacting the objects. And finally, a model for the grasp reward. So this is going back to these analytic quality functions. Given the known state and a grasp, there may be some distribution on reward due to randomization in physics. And so we built this big system to actually implement this model, where we had a repository of 1,500 3D CAD models. And in parallel, we had computation of robust grasp. So we computed grasp with high ability to resist arbitrary forces and torques. And you can see some of those colored by their quality up here. And similarly, rendered depth images of these objects in different configurations in isolation on a table in DexNet 2.0. And finally, associated the grasp with these locations and orientations in image space to form this training data set of 6.7 million images with binary labels, either positive successes or failures. And by looking at these images, you can already see some of the structure. The good grasp tend to have these surfaces that are parallel and opposite facing in the image. Mm-hmm.
Is the depth rendering assuming a fixed distance from the object?
So we assume that the camera is also in some known state here, but you can also randomize over the position of the camera, for example, and randomize over its parameters, something that we did in this work. Right.
Your depth perception tells you the distance is
right.
Yeah, I assume you're working with some sort of like reasonable working area.
Yeah, that.
Or whatever mid layer that you have.
Yeah, essentially, there's some bounds.
Yeah.
Mm-hmm.
Actually, it's a big question because generalizing this to, let's say, mobile manipulation, right, is different because particularly because you don't always know where the camera is. Absolutely.
Mm-hmm.
Cool.
That's more details I'll skip past. For deep learning, we use an architecture that was a modification on standard convolutional neural networks in image classification, where we took a grasp candidate and the depth image of the object. The grasp candidate specified with 4 degrees of freedom, the center pixel, the depth of the grasp from the camera, and the angle in image space. And then in one stream, transform this image based on the IJ phi of the grasp to create this training thumbnail, pass it through convolutional layers, and combine it with the output of the Z channel to predict the quality of a grasp. Training on the full DexNet 2.0 data set, we were able to get, at the time, 87% accuracy on a validation set with some contributions and some work by some awesome undergrads in the lab. We're now up to about 97% validation accuracy on this data set. So you can do very well on this. It's kind of like an MNIST of grasping data set at this point.
So
And
it would take you to make it 10 to minus 3 or 10 to minus 4 accuracy. Because if you really, and I have some experience in industry, if you really want to make impact in industry, that is the accuracy you have to have.
right, so for this, I think one of the limiting factors is actually the partial observability of the problem. So if the robot's looking at an image, and you can imagine just looking at this thing, and if I put a hole in the object right here, and then you only see this side, you won't actually know whether or not you're going to hit the surface based on an image taken from one viewpoint. So there's like a fundamental limitation in the data set, I believe. And I'm not saying that we've hit that ceiling yet, but I don't necessarily believe you can hit 10 to the negative 3 classification accuracy.
In the barcode situations, they have tested the ink that they were pressing on. They tested every single component on the camera, the lenses, the everything, LID. Otherwise, the customer just will not buy. And the paper.
Right.
You might say something about some of the industry you've talked to about that.
Right. So we've been talking with a lot of folks in industry, and in particular material handling objects that come out of bins and warehouses for sorting and for packaging. And they're actually, some small number of failures are actually tolerable if the robot fails and the object stays within the bin. The key is for the robot to maximize the rate at which it can get the objects out and not leave objects behind, depending on what the application is.
So, follow-up question. So you said that your problem is the partial observability, right? Is there any reason you don't say then, well, all the data is simulated, so let's simulate as if we had 3 depth cameras, right? One from top, one from each side. Could we then get up to a much higher accuracy? Right, so one of the things in the neural network or like image community, right, we typically say, well, we're only going to use the one image or one depth camera because that's all the data we have, right? But if you have a simulated data set, right, you're not restricted by the fact that everyone else is doing one camera image, right?
Right.
See what you need to do. I mean, if that's going to get you to 99.9% accuracy, right, that's the conclusion to then get to industry. So add 2 more depth cameras and you're good, right?
Right. That's a great point. I mean, that's a study that we probably should do just to look at that. I think that one other challenge, though, is when you have like objects in, say, a shelf or a drawer or heaps, then there's some fundamental occlusion of the objects by other objects. And I want to stress here also, this accuracy is about classification accuracy. And we'll show with some of the later results that you can get very high accuracy on the robot by still searching for the best grasp. So this is not measuring the same exact quantity as performance.
I think this is criticism. I think the reason we are speculating and trying to expand, your results is that we are so impressed by the current state.
Okay. Well, thank you. Thank you. Yeah. Yeah. So they're essentially planned beforehand. There is feedback, but it's sort of slow. So the robot can grasp, and it has to move its hand all the way back out of the way and look at the scene again. It would be interesting to include, for example, tactile or force sensors and try and understand ahead of time whether or not you failed. All right. I'll accelerate my explanations here a little bit. Okay, so that actually led nicely into this last bit of, okay, how do we actually use this neural network to plan grasp on the real robot? So we need some search algorithm to look over different candidate grasps and find one with the highest predicted probability of success. We used a particular derivative-free optimization technique called cross-entropy method, where the idea is to first sample a set of candidates. So this is sort of a random set of graphs that intersect some blob of points above the table. And then we could iteratively score all these graphs, fit a distribution to the ones that are most likely to succeed, and then resample from that fit distribution. And you can see over 4 full runs here, we can actually find this grasp where the gripper fits in this tiny hole or opening in this industrial part. So I want to talk a little bit about our physical benchmarking system. That's been a big part of my PhD. In DexNet 2.0, we set up a benchmark where the robot was presented one object in isolation on a flat tabletop at a time. And the goal is to simply grab, hold, move the object, and keep it in the gripper during a shaking operation. We did comparisons here with over 1,000 blind physical trials, so the person running the experiments did not know what method they were testing. We tested performance on 2 different data sets. One we called the training objects, which were adversarial because they had smooth curved surfaces or complex collision geometries that made it hard to find robust grasps. The reason we called these training objects is because we ran a study where we actually used the known 3D shape of these 3D printed objects to train a neural network that had only actually seen these objects. So you could see how well it performs with actual full knowledge of the shapes that it'll see. But we also tested performance with 50 novel objects not ever seen during training, including objects with deformations, some specularities, transparencies, et cetera, that make them hard to model for this physics simulation and to sense. On the training objects, we found that we could perform similarly to a registration-based system that estimated the pose with that system I described earlier up to about 4 millimeters of translation. And excitingly, it was about 3 times faster than that registration system with about 3 times less time spent engineering the speed of the system. I worked on that registration system for about like a year before giving up on it, actually. So I thought this was a big result. And then when we went to novel objects, excitingly we found that it had a very high success rate on even complex objects like this glue gun and this shoe. It seemed to be very good at finding grasp affordances that enabled it to grasp objects very different from what it had ever seen during training, including this cloth. And surprisingly, we also found that it did pretty well out of the box with heaps of objects. So when you put a bunch of objects in cluttered configurations, it was still able to find pretty decent grasp points. And that's what led into the next line of this work. But in the interest of time, I think I'm going to just quickly talk about the high level of this and get on to some recent results. So we did several extensions, one being parallel job bin picking, so where the robot's actually presented this, has this black bin actually filled with a heap of tens of different novel objects not seen during training, and the goal is to pick them out one by one, move them out. So just a little bit about this. Oh, sorry about that. We built a system for dataset generation that essentially is dynamic simulation to drop objects in virtual heaps. And we could use that along with the method I described earlier to generate training data sets. We use PyBullet for simulation here. But in theory, you could use a number of different simulators. So I'll jump past this. The other extension we looked at was to actually expand the range or the set of objects that the system could handle. So we noticed that there's actually a relatively broad class of objects, such as these big flat boxes and packages that were difficult to handle with the parallel jaw gripper, largely because of limitations of that particular gripper is narrow enough that it couldn't necessarily fit around the objects. And in industry, many people actually use a suction cup with a vacuum tube that sucks air through to grasp objects. So we extended our method to suction cups by making an actual model of compliant contact for suction cups. So we made this spring mass system that can project onto the surface of an object to detect whether or not a seal would be formed, leading to a change in pressure that would allow the robot to hold an object. The second bit of our model was analyzing whether or not once the robot established a seal on the object, it could resist given forces and torques on the object. And one interesting point about this that relates to the earlier discussion is that with a suction cup grasp, there's almost always a force and torque that is sort of very adversarial to the grasp, because if you pull tangentially the suction cup, it only has friction to hold on the object, as opposed to the parallel jaws. So we actually looked at whether or not it could specifically resist task-specific wrenches, such as gravity or other random perturbations. And with this, we generate a similar data set. We found that on objects with complex curvature, we could get some significant wins over common heuristics, such as targeting planar surfaces near the centroid of objects. And that's partially because our system could detect these points that perhaps sort of naturally trade off the ability to form a seal with getting near the center of mass and resisting gravity. This is just showing that working and operating by itself. And this is with no segmentation. So the robot sees a point cloud of this bin and generates a bunch of candidate suction points, pixels in the image, and then scores them and goes in. So I'd like to spend as much time as I can talking about this last bit, which is about how do we actually learn policies that can decide between these two grippers and maybe even extend to more heterogeneous grippers, such as soft hands or others. And the way we went about this was to sort of leverage everything I'd done in my thesis up to this point, have two different quality functions, one for each type of gripper, and take the max over each in order to decide whether or not one gripper was better than another, given some image of objects in a bin. One challenge we had to tackle here was actually calibrating the rewards so that they're measuring the same thing. So I went over that very quickly, but I noted that the suction cup was analyzing resistance to gravity. Earlier work had a different kind of metric looking at generic ability to resist forces and torques. And so we had to go back and reconsider our analytic model to have both of these types of grippers measure the same thing. By leveraging basically differences in contact models to form a wrench space and having one reward function that operates on this generic entity of the space of forces and torques a grasp can resist. We did some systems work and actually found that we could generate full training data sets containing, here we had two grippers, so we had 5 million data points in total, and trained from scratch on data generated from simulated heaps, with only about 2 days of data set generation on a standard desktop. And one other thing we did here was actually to tackle this problem we had of repeated failures. Here you see it, one of the older policies grasping a spoon over and over. And actually use an online error recovery system. And this is the brainchild of Matt Model, Mike Danielchuk. And the idea here is that if the robot fails and it can detect that it's failed, then it can remember not to try and grasp in the same region on that same shape. And could even push or perturb the scene to make more grasp affordable. So in experiments, we did extensive experiments over this past summer to characterize how well this DexNet 4.0 policy that decides between suction cup and parallel jaws compared against other methods considered in the literature. So we compared against two heuristics that were designed to reflect heuristics that were commonly used in the Amazon Robotics Challenge. Because this is actually one of the motivators of this work was seeing what people were doing there, always using a suction and parallel jaw gripper in unison. So we had suction by itself, a decision between the two based on some heuristics, and also using DexNet 2 and 3 in a composite policy, but naively comparing their outputs to show that actually needing a calibrated reward function or having a calibrated reward function can help. I think the most interesting result here is that, well, we broke performance into 3 data sets of objects in increasing difficulty. Level 0 is easy. Level 1 is slightly more challenging, more common object with skin pack and some transparencies. Level 2 has very complex geometries such as the Yoda. This package of scissors was very difficult, and so on. And I was particularly excited about this result. On these typical objects with 25 objects in the bin, it could reliably clear all the objects out one by one with 95% grasping accuracy. And that led to, that was about 310 picks per hour, successful picks per hour that the robot could remove one object at a time from a bin, which is significantly faster than the Amazon Robotics challenges. There is some differences between the comparison that I'm happy to talk about offline, but there the rates were more like 100 picks per hour. And I was really excited that our experimental rig got a lot better over the course of my PhD. So we actually have videos of every single experimental trial. So if you don't believe the results, they will be online, and you can watch all the videos if you really want to. We also looked at whether or not the results extended to larger heaps of objects. So we did an experiment with 50 objects, basically the bin full to the brim of objects. And here we could still get about 90% success. With a memory system, we were able to recover from a lot of the failures on these very hard objects. So this is showing on the level 2 objects what our success rate was before, including memory and after. And before, we're actually only about 60%, but by avoiding these repeated failures, we could actually get up to about 80%. And this is showing the policy running with the full memory system, just to give a sense of what this looks like. Although the memory system might take a while to kick in, so I'll step ahead. We've also done some studies on the value of actual real data in this application. So we've done so many experiments and demonstrations that we had about 15,000 data points from the real system with like actually decent ground truth success labels. And we actually found that it was very difficult to use this data and get a performance increase. So we tried many variations on fine tuning and did not actually see any significant change in performance across the method. So I think that's a very interesting avenue for future work. How do you do transfer learning to best leverage real data? It seems like a naive approach, doesn't work, but I do think this data is valuable. Okay, so a little bit of discussion. We're studying whether or not this can be used for other types of manipulation. So one is with these primitives called push cages, where the robot sort of traps an object and can slide along a table. We've done some studies on using this to reorient objects. So a particular task similar to the peg and hole that Rujna mentioned earlier, of just changing the pose of an object. There's some promise there, but engineering for many other tasks remains to be seen how challenging that'll be. We've been doing some studies with how to use this with other sensory modalities. And we've also released the code to see whether or not this can transfer to other robots and what would need to be modified in order for this to work on other robots. We've had, in collaboration with 4 industrial partners, we've actually been able to run this on other physical systems. So we're very excited about that, and we're excited for other people to give it a try. So I'll conclude with a quick statement here. One of the big points behind this work is that I think models are not necessarily contrary to learning, but actually can be used in conjunction with learning. And one way that we've studied in this work is that to basically reconsider the way in which we use models. The assumptions of a model used to, say, score candidate grasps are not necessarily the assumptions that the grasp planner has to make when the robot actually goes in to attempt to grasp. So we don't actually have to go from image to infer the perfect state that the robot or that the models like to operate on, but instead could actually use models to generate a higher level reward signal and do discriminative learning. And I also want to note that this work is not orthogonal to something like reinforcement learning either. This is about thinking very carefully about how you would say build an OpenAI gym environment that could transfer well from simulation to reality rather than using one out of the box and hoping that it works. I think it's important because I think that if you're trying to do simulation to reality, you do have to think about what the simulator is. And I think if you want high reliability in what you learn in the output, then it's important to consider the environment you're learning in as well as the policy, not just the policy. All right, well, I guess that is all. We ran a little over, but I'm happy to take any other questions if anyone has them. Thank you.